Chapter 2, the classical wave equation. So our journey into the heart of quantum mechanics truly begins in the pivotal year 1925. So in this remarkable period of scientific creativity, so two physicists, you might know both of them very well, Erwin Schrödinger and Werner Heisenberg. So they independently developed the first complete and general formulation of quantum theory. So while their theories were ultimately shown to be mathematically exactly equivalent, but their initial approaches were strikingly different. So Heisenberg, let's discuss the Heisenberg approach first. So he pioneered a path known as matrix mechanics. So his approach was highly abstract formulation that represented the physical properties such as energy and momentum as arrays of numbers called matrices. So I guess you already learned the matrix in fundamental mathematics class, right? First, like freshman class. Okay. So it was very powerful, but still conceptually very difficult to understand and quite abstract. So people think that Heisenberg's approach highly departed from classical our intuition. At the nearly same time, Erwin Schrödinger, so he developed what we now call wave mechanics. So his approach was built on the Louis de Broglie's radical idea or hypothesis that particle also has a wave-like nature. So you remember the wave-particle duality we discussed in the previous lecture. So Schrödinger was trying to find a wave equation that would govern the behavior of the matter's wave-like nature. So to do this, he turned to a very familiar classical equation that describes the motion of the wave. So this is the form of the partial differential equation, and he tried to solve that partial differential equation to understand the motion of the wave. So actually, the motion of waves can cover from the vibrating string, such as the guitar or violin, to like the light of the matter. So therefore, to understand Schrödinger's revolutionary formulation of quantum mechanics, we must build our understanding in classical wave equation first. So in this chapter, we will step back from quantum mechanics and try to understand and examine the classical wave equation. So you might feel it is more like a physics lecture, but yeah, still we are in the path of the understanding of quantum chemistry. So section 2.1, the title is the one-dimensional wave equation describes the motion of a vibrating string. So the important keyword is vibrating string and wave equation. So to begin with our study of quantum wave mechanics, we will start with the most intuitive and classical example, the motion of a vibrating string. The vibrating string. So maybe some of you can play guitar. Anyone? No? So normally the college students can play guitar, right? like back in 1990. Okay, well, anyway, so but still you know the how guitar looks like, right? So imagine a guitar or any other instrument has a string. Then there are two ends, fixed points, and we have let's say that this axis is x-axis. So one hand we have a fixed point for x equals 0, and the other point is also fixed at x equal L. So the length of this string should be L. And if you buckle the string at some point, then you can expect the string to vibrate something like this. Or if you buckle the string at different point with a different to the different strengths, then you might expect something like very complex string, something like that. Anyway, our goal is to mathematically describe the shape of this string as it vibrates over time. So we can do this by defining a function, displacement function u, which depends on both the position of the string and the time, evolution time. This is displacement. So this is simply how much the string is displaced from the x-axis. So you can think like this is the u xt. So this is simply the vertical displacement of the string at any given position x along its length and any instant time t. Because the string's shape also depends on the time, right? So its shape changes along time t. And the equation that governs this motion is the classical one-dimensional wave equation. So classical one-dimensional wave equation. So we are not going to derive the classical one-dimensional wave equation, but still you can do this if you want, and you can find some clue at the exercise problems. So chapter 2 has a lot of exercise problem, and one of them try to show you how to derive classical one-dimensional wave equation. So if we just write down the final result. So this equation says that the second derivative of displacement u with respect to the position x should be equal to the second derivative of displacement with respect to time t and multiplied by 1 over v square. So v should be the velocity of the propagating wave. So let's break down what this equation tells us physically. So first, the left side. So this is the second derivative of the displacement with respect to the position x. So this describes the curvature of the string at a specific point x. So the larger value means that the string is more sharply bent, right? So the higher the left term means that you pull the strings harder. So compare like soft. If you pull the string really hard, something like that. And the term on the right, So this represents the vertical acceleration of that same point on the string. So this is the second derivative of the length with respect to the time. So you can expect that this represents the acceleration. So if we plug in those physical interpretation into the equality, you can interpret that the wave equation makes a profound physical statement that the acceleration of any point on the string, this is directly proportional to its curvature at that point. So, and the constant of the proportionality is 1/v square. So our lecture is still chemistry-based class. So if you cannot fully derive this equation, so still it is okay. But now we have to accept, and we have to accept and be more familiar with this equation. So this wave equation has two important mathematical properties. So the first is mathematical properties of just mathematical properties. So the first property is this is linear partial differential equation. So it is actually a partial differential equation, right? Why is it partial differential equation, not just the ordinary differential equation? What is the difference between partial and ordinary differential equation? Anyone? So raise your hand if you took the mathematics for chemistry last year. Anyone? Oh, I guess there should be some students. Yeah, because I was teaching the mathematics for chemistry last year, so I already taught the difference between partial and ordinary differential equation. So someone should know this. Okay, the difference between partial and ordinary differential equation is the number of independent variable, right? So actually the classical one-dimensional wave equation is partial differential equation because the displacement function u has two variables, the independent variables, the position x and time t. So now we understand the partial differential equation and what is the linear partial differential equation. So if you examine the shape of the classical one-dimensional wave equation, so the function u and its derivative appear only to the first power. So there are no terms like the square of this property, right? There is no term like that. So every derivative and the function itself has the first order term. So that's why we call the classical one-dimensional wave equation is linear differential equation. So actually the linear differential equation has a very important issue or important property that if you have two valid solution for this partial differential equation, something like u1 and u2, then their linear combination U3. So the linear combination of two different functions should be something like U1 multiplied by some constant C1 and U2 multiplied by some random arbitrary constant C2. Their sum should be, their sum U3 also be a valid solution to this partial differential equation. So this is important feature, and so this linear combination. So the linear combination of independent solution can also be the valid solution of your partial differential equation. That is the basis for the principle of the superposition. So nowadays you heard the terminology superposition a lot, right? So these days all the media says about the quantum things, quantum information, quantum mechanics. So the superposition is quite everywhere. So we are going to learn the superposition later in this lecture. And the second important property is boundary condition. So our general one-dimensional wave equation will give you the general wave equation, right? So it is not describing the particular situation. So to describe our specific string that has the both ends at x equals 0 and x equals L, we need to apply our geometric constraint known as boundary condition. So since the string is fixed at both ends, so its displacement at these points must always be 0, right? So you are fixing both ends of the strings. So we cannot really say anything about the displacement along the arbitrary x. But there are 2 points that we can say that these points are fixed. So displacement at x equals 0 should be 0, regardless of time. Similarly, we can say that displacement at x equals L should be 0 for any time. So actually these conditions are essential for finding the specific solution that correspond to the standing wave in our situation. And you might realize in chapter 5 or chapter 6 lesson that the quantization is actually the result of applying boundary condition to any problem. So we already learned that, no, actually not, we haven't studied yet, but so in the next lecture, I guess. So in a particle in a box problem, the quantization is simply the result of restricting our particle in a specific box. Okay, so boundary condition also we discussed. So now we understand the structure of one-dimensional wave equation. Now we move on to next page to solve this wave equation. So as I said in the previous page, so in this section 2.2, we are going to solve the one-dimensional wave equation, and we are going to employ the techniques called separation of variables. Okay, the separation of variables. So we will tackle the wave equation using a very powerful technique called separation of variables. The core idea is to assume that our solution, displacement u, which has two independent variables, x and t, this can be simplified. How? We assume it can be factored into a product of two separate functions, each depending on only one variable. So the one function for the position, x, and the other one for time t. So the separation of variable is quite straightforward mathematical techniques. So we have two independent variables for the displacement function, but now we have a displacement function. The displacement part that only depends on the position x, and the temporal part that only depends on independent variable t. So substituting this assumed solution back into the original wave equation, 1 over b square so instead of u, we are going to put x multiplied by t into here and here. And we are going to performing the derivatives. And you know that the left part, this only involves with the position derivative. So the temporal part, capital T, should be considered as a constant. Then this will gives you t, and now we are not using partial anymore. We are getting back to ordinary differential equation. So no more partial. Now we are going to use d squared d squared x over dx squared. 1 over v squared, and similarly so as I mentioned in previous, the important difference is the partial notation becomes ordinary derivative t. And compared to the original equation, this looks might a little bit more complicated. But if we divide both sides by u, still we are going to use that the displacement is given as the x multiplied by t. Then this will give us something like this. Now we are very close, we are almost there. The separation. So this equation represents a crucial insight. The left side is a function of x only, because the capital X is only a function of x, right? Small x. And the right side is only a function of time t, right? The capital T is only a function of time t. We also know that x and t, they are two independent variables, right? Variables. There should be no correlation between the position and time. They don't have to be, right? So they are independent variables. So the only way for this equality to hold true for all possible values of x and t is if both sides are equal to same constant called separation constant k. This is the only possibility. So by using separation of variables, we can break down our single complex partial differential equation into two much simpler ordinary differential equation. So one partial differential equation is now become two ordinary differential equations. So these two ODE are, the first is spatial equation, d square x dx square minus kx equals 0. The second is the temporal equation, d square t over dt square So these two ordinary differential equations are quite easy to solve. So in the next page, we are going to solve these two differential equations. So analyzing. So let's analyze the behavior of the ordinary differential equation depending on the separation constant k. So depending on the value of k, we are going to have three different situations. So first is the positive k. The second is k equals 0. And the last case is the negative k. So these three cases cover all possible values of k. So we will solve the spatial ODE for these three cases. And for sure, we still have the boundary conditions that are 0 and x equal L, the displacement should be 0, which means that for the spatial part, we can, due to the separation of variable, we can simply put that this boundary condition only applies to the spatial part. Okay, the first case, k equals 0. So if k equal to 0, our spatial equation just simply becomes, let's write down the spatial part equation somewhere here. First case is k equals 0. That means this spatial ODE now reduced to something like this. So the general solution to this ODE is x equal simple straight line. Just the first order polynomial solution. So for this general solution, we are going to find the specific solution for our specific problem. So we are going to apply two boundary conditions to this general solution. Then the first condition is when x equals 0, the capital X also should be 0. That means, so from this we can say that the y-intercept of the solution should be 0. And when small x equal to L, the capital X also should be 0. AL should be 0. That means, so L cannot be 0, right? L is the length of the string. That means the slope of the straight line should be 0. So both constants should be 0 for the separation constant 0. That means we have a solution x equal simply 0. So this solution is also mathematically valid solution, but are we interested in this solution? Actually, this equation describes just a string without any motion, right? So this is not our interest. So this is called some trivial solution. And the second case, the positive separation of constant variable. Separation of variable constant. So those words were mixed in my head. So positive constant, we can write something like that to explicitly showing that the separation constant is positive. So the spatial equation now becomes this is one of the prototype examples of ordinary differential equation. You might already you already learned in the mathematics class. So this simple equation means that if you differentiate the capital X with respect to position X second time, then you will obtain the function itself with some constant k square. So that means the X should have some form of the exponential function with constant. So let's say this is the C exponential alpha X. So this is some feasible solution for this ordinary differential equation. So let's plug this solution into the ordinary differential equation, and we can find the value of the alpha. So you will realize that there are two possible values for alpha, which are plus and minus k. So the one-dimensional wave equation has two important mathematical properties. The first, did you remember the first property we discussed? So it is linear differential equation, right? So if you have a multiple solution, then the linear combination of all the possible solutions can be also a solution to this problem. So if you have two choices, then your solution should look like so you have two different solutions, then their linear combination multiplied by two arbitrary constants and their sum. This should be general solution with a positive constant k. So I'm not going to show the details how we apply the boundary condition for x, but still you can do this by yourself. Then you will realize that in this case also x becomes 0. If we force the general solution to satisfy the two boundary conditions that we have. So as I said earlier, so x equals 0 means the no motion in the string, and it is not our interest. So we are not going to accept this solution. So since the cases k equals 0 or positive k only lead to a non-moving string, and so we have the only possibility for a physically meaningful and realistic solution. We can expect that only meaningful solution can be obtained from the negative k, right? So let's discuss that in the next page. Section 2.3 is, the title is Some Differential Equations Have Oscillatory Solution. So this is really important keyword. So as we determined in the previous sections, a physically meaningful solution for the one-dimensional vibrating string requires the separation constant to be negative, because that is the only possible case. So let's set this constant as negative k squared. So to make it explicitly negative. So this transforms our spatial differential equations into some like something like this. Oh, sorry. So I use beta. So I don't want to confuse using the same notation for the positive and negative constant. So this is a linear second order ordinary differential equation with constant coefficient, right? So we already know how to solve this problem. We have done this for just in the previous page. So no matter the constant is positive or negative, the procedure for solving the ODE is exactly the same, but the difference is the value of the exponent. So in this case, we expect the differential equation can be a general solution for this ODE, and you have to find the value for the alpha. You can simply plug this into differential equation, and you can find that the alpha should be plus minus I beta. So now we have some weird notation I. That is because when we plug this into here, we will have alpha square, exponential alpha x, and beta square, exponential alpha x should equal to 0. The exponential function can never be 0, right? It approaches to 0, but it never becomes 0. So we can divide both sides by exponential alpha x. Then we have the sum of alpha square and beta square should be 0. So that leads to the value of the alpha equal to plus minus I beta. So I should be the square of I should be -1. So this is the notation for the imaginary number. So we have two possible cases, and the general solution should be the linear combination of these two possibilities. So x should be c1 exponential I beta x, c2 exponential minus I beta x. So this is general solution. So before we move to the step to apply the boundary condition, let's recall the Euler's formula to simplify this complex equation. Euler's formula. So if you want to know more about the Euler's formula, then you can ask GPT, and or you can search the textbook if you have them. And the Euler's formula gives the exponential plus minus I zeta should be equal to cosine zeta plus minus I sine zeta. So Euler's formula allows us to convert from the exponential function to trigonometric function, or you can combine the trigonometric function to exponential function. So for sure they are mathematically exactly the same expressions, but sometimes the exponential function might be more convenient to handle, or sometimes the trigonometric functions are easier to use. So we are going to select the exponential form or the trigonometric function form depending on your situation. So applying this formula to our solution, like we have exponential function for this and this, then our cosine beta x plus sine. So first exponential function should be expanded like this, and the second part cosine beta x minus I sine beta x. This is the expansion of second exponential function. Now we can regroup the terms. So we separate the real part. Real part should be this one and this one, and the imaginary part, this one and this one. So we can separate the real part and imaginary part. So C1, C2 cosine beta x, imaginary I, C1 minus C2 sine beta x. So it is more like the complex number. So real part and imaginary part. Since the constant for the linear combinations are arbitrary constant, so we can define a new constant, something like C1 plus C2 as capital A, and I multiplied by the difference between C1 and C2 can be. So there is no problem like changing the arbitrary constant into another form of the arbitrary constant. So our final form should be A cosine beta x plus B sine beta x. So we have done this just for the just for us. We are more familiar with the real number, and we feel more comfortable with the real number than the imaginary numbers. So that's why we transform the exponential solution into trigonometric forms. And finally, we are going to apply the boundary conditions. So you have to remember that when you solve the differential equation, which means you solve the Schrödinger equation, then you have to find the general solution first, and then you apply the boundary condition to find the specific solution or particular solution to your problem. So boundary conditions. So the first boundary condition is this one. So that gives you A cosine 0 plus B sine 0. That means the cosine 0 should be 1 and sine 0 should be 0. So it should be A, simply A. And our boundary condition indicates, says that it should be 0. So that means the constant A should be 0. So with A equals 0, now our solution is simply B multiplied by sine beta x. So let's apply the second boundary condition. X equal L. I mean small x equal to L. The capital X should be 0. So that will gives you 0 equal B multiplied by sine beta L. So now we have two different possibilities. To make the multiplication of these two functions to be equal 0, we have two possibilities. So the first possibility is B equals 0. But this solution is nothing, right? I mean, nothing really interesting. So still we came back to the string with no motion, right? So we are not going to accept this solution. The second possibility is sine beta L becomes 0. So this only happens when the argument of the sine, the beta L, is the integer multiple of pi, right? If you recall the shape of sine function, it looks like something like this. So sine function becomes 0 at x equals 0 and pi, 2 pi, something like that. So this means the argument of the sine function, beta L, should be the multiple of the pi, integer multiples. So n should be 1, 2, 3. So I said that the argument of the sine function should be the integer multiples of pi, but we are restricted to ourselves to the positive integer because we are dealing with the shape of the vibrating string, right? So the negative integer doesn't mean anything to our case. But mathematically still, mathematically n can be any integer number. So let's, I want to emphasize this part. So actually this step quantizes the possible value of the beta, right? So remember where we introduced the beta first. So if we go back earlier. So we introduced the beta as a separation constant. So fundamentally, the beta can be any values. I mean, any real number for here. But when you solve the when you solve the wave equation and you apply the boundary condition, now the beta cannot be any value. Beta should have some form of discretized values, right? So beta can be like L pi over L, 2 pi over L, 3 pi over L, something like that. Only some specific allowed values can be candidates for beta. So this gives a set of allowed solutions, or more scientific terminology, it's normal modes or allowed solutions for the string's shape. So we just use the capital X for the the part for the capital X for the part to be related with the position X. But now we are going to add the subscript n to make sure that the allowed value beta is dependent on some quantized number n. So the constant also needs to be indexed with a quantized number n, and sine n pi x over L. So this is the particular solution for describing the vibrating string in our problem, which has the length of L. So every strings or any existing string should follow or should be described using this function. So it is quite interesting, right? So we think that the motion of the vibrating string is quite continuous and it looks like just random things. But actually the motion of the vibration string is quite quantized, and there are some set of allowed solutions which called normal modes.